Hello and welcome back to the lecture on applied econometrics. So we have been talking about a very interesting topic called the regression table, and we're trying to understand the different components of regression table. So the previous lecture we explained the first part of the table, which is the ANOVA part of the table, and we said that in the next lecture we're going to explain the hypothesis testing part of this table, and this is the second part that we're going to talk about. And here we actually what we're going to do is basically hypothesis testing. Now, hypothesis testing of what? Basically, that's what you're going to see in this lecture. So we have all these different explanatory variables like exercise, age, right? And we also have the constant term. Now what we are trying to do here, so we have to, let's try to actually look back what we did when we actually plotted you remember that, let's say we are regressing with one explanatory variable x, all right? And we get some line which is like which will somewhat approximate the, all the points that we have on the plane. And we're not talking about multiple regression now. Let's say it's just a simple regression with one explanatory variable, and we get a estimate of this beta 2 coefficient, right? That which is basically the slope of that line. Now remember what we are doing here is that it is a bunch of data that you got. You took a sample from a population. You never get the entire population, that you already know. So there is a population here, and all that you can do is you can take a small sample out of that population, and when you are running a regression equation, you again have to sort of depend on the same mechanism where you have a small amount of data taken from the population, which is called sample, and you run a regression line, or you basically get a regression equation using that sample data. All right. So this particular regression equation that we see here is essentially is a regression line that you obtain using your those sample data set, right? So you can also call it, sometimes it is called sample regression function, okay? So sort of sample regression function, SRF, sample regression function, this, and whereas the actual regression equation that you might have, or that you actually have, which you will never know, is a population regression function. We can just use these terms sometimes. So here what you get is that, so here you are essentially getting the regression equation from the sample. So the beta 2, we normally denote small b or b, whereas for population we actually denote as beta. So for sample is small b, whereas for population is beta. So here what we get is this beta coefficient, which is an estimate. So which beta, so the b2 is the estimator of the beta. Okay, so you never know beta, but you can know b, right? And if you can know b, you can estimate beta. So that's the mechanism that we are trying to follow here. Now what we are trying to do here is we are trying to see if that b, the coefficient that I obtained from my sample, whether that is able to explain the population parameter, which is beta, right? So that is why we need to do a hypothesis testing, whether my b is able to sufficiently explain beta. Okay, so how do I actually do that? So essentially we create some statistic. We say, let's say it's a Z statistic. So Z statistic here, if I have, so say like if I'm using a normal distribution where my population parameters are known, I normally write b2. So this is my slope, and this is the population. If I would have known the population parameters, so the beta 2 would have been the population parameter, and you have the standard deviation. So that is how you would have gotten the your z value. Now your null hypothesis is what? Your null hypothesis is saying that the beta 2 actually does not have any significance. So your beta 2 is actually, H0 is saying your beta 2 is actually 0, right? Because that is what you are assuming. Your model does not have any, your variable or that explanatory variable does not have any power to explain the variations, right? That is your null hypothesis. And if your beta 2 is 0, so then your z is going to be b2 by st, right? So that is what your null hypothesis is saying. Now you actually create your confidence interval. You can take like whatever alpha value you want to take, 5%, 1%. Usually you take 5% for 5% confidence interval. You create you get your z value, and you create that confidence interval. And if you see if your z value is going beyond the confidence interval, you sort of reject your null hypothesis. So that's how you actually do basically the hypothesis testing here. Now this is for known population parameter. But this is an ideal case. I mean, you actually, what happens in reality, you never know the population parameter, right? You never know the population parameter, and then so basically what we have is that a known population parameter. So when you have unknown population parameter, you cannot really use a Z statistic. Let me use a different color for this part. So for unknown population parameter, what you use a T statistic. Okay, so T statistic where you actually use this. Again, the same idea remains the same. The only thing that differs here is the standard error term. So where you have the standard error, okay, which you actually estimate from the essentially you can write the unknown. You essentially estimate it from the sample. Okay, here also it is a standard error, but it is a known. We'll talk about standard error. Okay, so that's, and the remaining, so here H naught, once your H naught is equal to H naught is beta 2 is equal to 0, your T statistic is going to be beta 2 by SC unknown. Okay, now we'll essentially, this is what we are going to do. So we have this corresponding T statistic for each of these different beta, and we'll try to see whether they are significant or not. So we'll do the significance test for each of these different beta. So let us again go back to our regression equation or the table. So what we see here is this. So we have like different items. So we have different items. So one, we have our coefficients, we have our standard error, we have this T statistic, we have this p value, and then you have the confidence interval. So first let's talk about the coefficient. So coefficient, by now we have some fair idea about what a coefficient is, and we have actually, sort of explained this coefficient. We have these coefficients here where we have, so here my coefficient is B2, which is like explaining how much my this line, this fitted line is actually able to explain my y variable, right? Now, so all these different values, essentially what they are saying is that, so if I take exercise here, so what I will understand is, so per unit, whatever unit I have taken, per unit increase in exercise is going to decrease the cholesterol level by 0.73 unit. Okay, so that is what it explains, like any straight line equation we explain. So it is essentially the same thing. To what extent the variation of exercise is going to impact the variation of cholesterol level. Similarly for age also, it says that per unit increase in age will increase the cholesterol level by 2.5. So essentially it is again like the straight line where your change in x, per unit change in x, is you are basically measuring how much it is going to change the y. Okay, so it's 2.5 times. Okay, so that's the coefficient thing that talks about. So with multiple like regression explanatory variables, you have like on multiple dimensions, you can think all these different explanatory variables are increasing the y or basically influencing the y in different dimensions. Okay, now that's fine, but so just that you have some value, does that mean that you have to sort of end there? Of course not. You have to see whether these impacts are really significant, if they really are meaningful here. So how you really understand that? And that is, for that you actually need to consider all these different standard error, T statistic, and p value. Okay, let's look at the other terms. Let's first look at what is standard error. So standard error is something that is a little tricky here, and we have to keep keep in mind what these standard errors are. So standard error, I mean it sounds pretty much like standard deviation, but we say it's standard error and not standard deviation. So why is that? Is there any specific reason why we say that? We'll just talk about this. And how we really measure the standard error. Here we have actually explained this case of unknown thing and known thing, known standard deviation, unknown standard deviation, and how they're, so we'll try to see how they're related to the concept of standard error. Okay, so what happens, let's say we'll standard error. So what is happening here? Let us try to explain. So standard deviation is something is very straightforward. We know like how we actually get the sigma, right? Sigma is nothing but y 1 by n summation xi minus x bar square. Now that's fine, that's the standard deviation you got. But then you have to sort of you have to get. So we know that in this is the standard deviation. Let me actually write down deviation for. So when you already have all the values x, you know all the x's, you basically calculate the standard deviation. Let's say this is the we usually denote population standard deviation by sigma. Okay, so let's say we're talking about the population. Now, when we actually talked about this concept of estimation from sample, usually we know that it is not that easy to get the population standard deviation. So what we do here, we actually have to estimate from sample, and when we use the sample, we actually denote it as Sx, and when we denote it as Sx, what we do is we actually use 1 by n minus 1, right, for sample, because there are some approximations involved, and we explained where these approximations are coming from. So we write this, okay, and we sort of use this approximated value to the population standard deviation, okay, because that is how we sort of conceive the whole idea, how Sx could represent the population standard deviation. Now, there is another trick here. So when you are actually estimating from, like this, when you are doing this estimation thing, so you actually want to estimate, you actually have your estimator, the mean is fixed, right? So you want that, you actually want to have you actually want to draw different samples, and you want to get their standard deviations, and you want to actually get the the standard deviation of the means, not the individual item, okay? And to get that, to do that, to get the standard deviation of means, you actually have to draw different samples time and again from the observation. But if you have, if you just remember how we have sort of progressed in this development of, getting this regression equation or the minimization of error term, we really haven't done something where we actually draw the sample time and again. So this is an approximation that we use, and the moment we don't do that, taking the observations time and again, and actually, calculating the standard deviation of the means, we actually take all the observations in one go, and what we do is we essentially, it is a simulation that statisticians have come up with, is that you just divide it by square root of n, and if you do that, so then that will actually give you the standard deviation, so the standard error for mean. Okay, so what you write it as is x bar is equal to, say, 1 by root n into 1 by n, or let me 1 by n minus 1 summation of xi minus x bar whole square. So this is what we call as standard deviation or standard error of mean. Okay, so we are calculating the standard error from for the mean. So that is what we are more interested in, standard error of mean, and this is how we actually estimate. So for when you are estimating from sample, we simply divide it by square root of n, and similarly for here also, this is nothing but is sigma x by square root of n. So we essentially divide it by square root of n to come to this approximation. Just remember this. So this, so what we are actually calculating there in the regression table is that we are actually getting this standard error of mean, and since we are calculating from samples, we don't have the population parameters readily available with us. So we divide the whole thing with 1 by square root of n. Okay, and the expressions that you have seen there, all these expressions that you have seen there are essentially essentially this, where we have this 1 by root n into 1 square root of 1 by square root of 1 by n minus 1 into summation xi minus x bar whole square. So, that is how we have got the standard errors. Okay. So, these are the two. So, we have explained these two concepts, coefficient and standard error. Now comes our t. Now, t we have already explained. T is essentially, given our hypothesis testing, t is essentially B2 or the coefficient by standard error. So, if we do that, if we go back there and if we actually do that, so what we will see is, so t will be, so the ratio between ratio of this coefficient and standard error. So, ratio of these two. So, like let us actually do that. So, the coefficient for exercise is 0.739 by 0.326, it should be here 0.739 by point, how much was that, 236, 0.326, okay. So, 2.26 something like that, and since you have a negative sign here for exercise, you will also have a negative sign for your t statistic, right. So, that is how we get all the different t statistic. Okay. So, you get for different coefficient as well as the constant term. So, you basically divide, we take the ratio of coefficient and the standard error. So, that is how you got the t statistic. So, then so you have got that. Now you got all the three terms you need. Now, we come to the fourth item, which is the p value, and that is very important. Like in the previous case, we have seen how to get the p value for f statistic. We will get in the same manner the p value for the t statistic as well. Only thing that will differ is that we will, in this case, we will see a t table instead of a f table, right. So, let us do that. So, let us actually try to find how a t table looks like, and I actually have done that for you. I actually got the t table here. Okay. So, we have to see how to see a t table. Okay. And for t table, you will see here we are talking about only one degree of freedom, like one, the degree of freedom in the column, not in the row like we had for the f distribution. And that is because in t distribution we are only talking about, so we are not taking a ratio of variance or anything. We are only thinking about the one sort of distribution here, and we are just taking into account the total number of observations. We are not fitting any model, we are not actually calculating residuals, so we do not have to get into k or n minus k minus 1. All we have the n number of observations. So, we know that it is an estimation problem, so we have to have one thing fixed, one parameter fixed, which is because of that we will have degrees of freedom equal to n minus 1. So, here we have in our case we have how many observations? We have 12 observations. So, my n minus 1 would be 11 and the degrees of freedom. So, here we usually, so it is a two-tailed test because we are just trying to check if the equality holds. We are not talking about greater than, less than anything. So, we are basically doing a two-tailed test. So, when you are doing two-tailed test, we are, and it is a 5%, alpha is 5%. So, we have this and this is 11. So, what we get here is the corresponding t value is essentially 2.201, corresponding t value is this. Now, what I will do is I will draw a t distribution, and I will actually try to see where my observed t value falls vis-a-vis the critical t statistic value. Okay. So, let us do that. So, I will sort of draw the t distribution, and we know that t distribution is somewhat similar to, it looks somewhat similar to normal distribution, though it is not a normal distribution. And I have a t critical here, and the moment my t statistic is here, like it is, if it is, depending on where it falls, if it falls right to the t critical, so the p value here would be very low. And when the p value is very low, we have explained how we can explain the the p value. So, if it is very low, then we say that the null hypothesis is rejected, and the reason is, like, we can explain in different ways actually. We will again recap the p value, is very critical in all the things that we are doing. So, the moment I have a low p value, it means that p value is actually defines the sort of, the strength, I can actually use this definition, strength of evidence against is the alternative hypothesis. So if my p-value is very high, let's say I have my p-value, like my t statistic here, and my p-value, like the area under the, area right to that t statistic is very high. So that means I have lots of evidences that are going against the alternative hypothesis. It means that my model is actually not explained by my alternative hypothesis, but it is rather explained by other randomnesses. So which is essentially kind of telling that your alternative hypothesis you can reject. So essentially your strength of evidence against alternative hypothesis is very high, right? And that is why you do not reject the null hypothesis. You say that your null hypothesis, whatever it is, you are saying that it is, you cannot reject that. So this is something is a p-value, or other way you can think that, like if you don't, this is one explanation, this is one way of looking at it. Other way of looking at p-value is that, well, if you have like the evidence that you have got is like, which is sort of telling where the, about the alternative hypothesis, it is so extreme here, it has come so extreme that, say, from your null hypothesis value, that even after giving so much of, like the interval, like width of the interval, your evidence is even falling beyond that. So the moment your evidence is falling even beyond that, you say that, you kind of say that this is not something that you can say that it is close to null hypothesis. So your alternative hypothesis is far, far away. So you're essentially you are bound to reject the null hypothesis. So that is where you actually, this is different ways of looking. This is kind of feeling how the p-value, actually talks about. Okay, so we basically calculate all this, this t critical, and we see the t statistic. So now we found our t critical to be, 2.201. Okay, so our t critical is 2.201, and in my regression table, what I found my t statistic to be 2.26. So it is 2.26. Okay, 2.26 for exercise. For exercise, you have 2.26. So it means that it is actually falling somewhat right to the t critical, and the moment it is falling somewhat right to the t critical, you will say that my, I will reject my null hypothesis. And how do you actually get the p-value? Here you see the p-value is 0.05. We can actually go to the t statistic table again, and to make some sense of this, so for 11 degrees of freedom, we are talking about area in two tails, so it is 2.201. If it is, so we have this, we don't have value for all the different areas. We have like area for 2%, 5%. So we have 2.201, 2.7 if it is 2%, and it is 10. So it is 1.79 if it is 10%. So essentially, if you see that what your p-value or for t, the t statistic, what you observed is 2.26, which is coming very, very close to this one. Okay, which is coming very, very close to this one, and that is why you kind of say, I mean, it could have been a little more here. So that is why you can say that, your p-value is like approximately 0.05. It could be like 0.046 or something, 748, but we don't have all these values, so we approximate it as 0.05. Okay, in this. Now for age, your t statistic is 9.48. Now you already have calculated your t critical. So when you have your t critical, and you have to sort of, your calculated t statistic is 9.48 for this term is your age. So it is again falling far right to your t critical, and that is why we can definitely reject that. Okay, even for the constant term, you have your t critical value coming out to be 5.34, and it is again like on the other side of the t distribution, you can actually show. So if you have like t critical here, and your t observed t statistic is coming here. T statistic is here. Okay, observed. Okay. So this is how we sort of see we actually calculate the p values and we take a call on whether to reject or not. Okay, the coefficients, whether they're significant or not. Okay, so we are done with all these different 4 terms. So here now we have done coefficient, we have done the coefficient. So we have done the coefficient part, we have done the standard error part, we have understood t, we have understood the p value. Now last part is the confidence interval. So once we do this, we are through with all this regression table. So how do I calculate the confidence interval, and that is what we have to see. So here we are kind of, usually we take 95% confidence interval, or alpha is equal to 0.5 or 5%, 0.05 or 5%. So when I'm creating a 95% confidence interval, so what I do is essentially I get a t critical value for 95% confidence interval. So we have already seen that. What is the t critical? We had this t critical is equal to 2.201, right? So we have already seen that the t critical for 95% confidence interval we will have 2.20. Sorry, just a second. Where is that for my 11 degrees of freedom, right? So this one, 2.201. All right. So what is the formula for my confidence interval? How do I actually? My formula for confidence interval is this. My formula for confidence interval. So the way I create the confidence interval is simply x bar t critical into standard error. So when I'm saying standard error, you don't have to, it's already, you have in your regression table is already calculated. You don't have to do anything about dividing by root n or anything. You just take the standard error and you get the t critical and you basically compute the confidence interval. So what it will be, so your x bar for, let's say we do it for exercise, or let's say we do it for age. So 2.516. So 2.516, t critical 2.201, and the standard error that we had for this is 0.265 or 0.266, let's say 0.266. Okay, and if I compute this, 2.56 plus 2.201 into, I have to use the standard error, is at 0.326, and it will give me 2.516, 2.201, 2.265, oh, just a second. Oh, I have actually taken a wrong one. 0.265, 0.265. That is going to give me something around 3.09 or 3.1. Okay, so let me just increase the font here. So it's approximately 3.1, and that's precisely what you see, 3.1. And if I just subtract this, I'll get the the other side of the confidence interval, which is 1.93, and it's like 1.91 approximately. So essentially that is how we calculate the confidence interval. Now I'll ask you a question. So what I'm trying to do here, so suppose I have calculated the confidence interval and it is showing that the range is from, say, for the first one it is minus 1.47 to some minus 0.0005, and for the second one 1.91 to say 3.11. So what is really talking about? So if you look at it carefully, what it talks about, say for example for age, so what it is talking about is that the confidence interval is actually on the right side of the 0. So it is not containing 0. Even for the first one it is not containing 0, or even for the third one it is not containing 0. So everywhere it is excluding 0. So what it means is your null hypothesis was that the mean value of all these the different coefficients that you were estimating, in null hypothesis was 0. So the moment your confidence interval is not including 0, it is excluding 0. So that means that your estimate, the thing that you are estimating, that is actually not containing 0, but it is falling somewhere on the right or left. So 0 is not an option for it. So when that is the case, you call it that your alternative hypothesis is actually sort of explaining your model. So you kind of reject the null hypothesis, right? So in all the cases, you see that your confidence interval is not containing 0. So that is what you see here, okay? And that's what you need to remember. So you will see that, of course, they will have a correspondence between the p-value and the null and the confidence interval. So if your confidence interval is not containing 0, your p-value is also going to be very, very low, okay? So that's about this these 4 items. So one more thing I would ask you is that why do we use a t statistic and not a z statistic? So we use a t statistic and not a z statistic. And if you recall, what we sort of started this lecture with is that, well, your population parameters are not known. So you have to basically calculate your you have to estimate your population parameter from the sample observations, right? So we use Sx instead of sigma x, right? And since we always do that, because we never know the population parameters, we use a t statistic instead of z statistic, okay? So in all regression table, it does not matter what is the number of observations you have, you'll always use a t statistic for, sort of testing the significance of all these different, explanatory variables. So all right, with this, I think we can end this lecture on regression table, and yeah, from here we'll yeah, so that's end of this lecture.